RISC-V and AI acceleration. The dream of a truly open silicon ecosystem is currently clashing with the brutal reality of compiler optimization, where a single missing vector instruction can turn a cutting-edge AI model into a sluggish computational bottleneck. This is the frontier where RISC-V meets the demanding world of Linux-capable AI platforms. While the hype surrounding hardware like the Milk-V Pioneer is palpable, a forensic engineering analysis reveals a landscape defined by fragmented toolchains and the growing pains of a young instruction set architecture. When we evaluate the technical feasibility of running intensive AI workloads on RISC-V, we are not just looking at clock speeds or core counts. We are looking at the maturity of the vector extensions, or RVV. Unlike the ARM ecosystem, which has spent nearly 20 years refining its Neon and Helium extensions to provide predictable performance, RISC-V is still navigating the transition from draft specifications to stable implementations. For a senior engineer, this introduces a significant risk. The software libraries you rely on today, such as TensorFlow Lite or ONNX Runtime, might not yet fully leverage the silicon sitting on your desk because the GCC or LLVM compilers are still catching up to the latest hardware revisions. The engineering challenge becomes even more complex when we look at the Milk-V ecosystem. The Milk-V Duo and the Pioneer represent different ends of the spectrum, yet they share a common hurdle: the integration of proprietary or semi-standard NPUs. Many RISC-V vendors implement custom instructions to accelerate neural networks that exist outside the standard RISC-V ISA. From a functional standpoint, this means the Linux kernel must be heavily patched with vendor-specific drivers that often lag behind the mainline kernel. This creates a maintenance burden where the stability of the board support package or BSP is constantly at odds with the need for the latest kernel features. Consider the memory model. AI workloads are notoriously data-hungry, requiring seamless movement between main memory and compute units. RISC-V's approach to memory consistency and DMA management in a Linux environment can present unexpected latency issues if the software stack is not meticulously tuned for the specific SoC architecture. If the silicon supports an older draft of the RVV spec instead of the finalized 1.0, the performance penalty is immediate. You end up with a system that is excellent for academic research or early prototyping but lacks the industrial-grade reliability required for a mission-critical production environment. From an engineering management perspective, the feasibility study must conclude that while the path is open, it is not yet paved. The technical debt associated with porting optimized BLOS or LAPACK libraries to a new architecture is non-trivial. It requires deep expertise in assembler-level tuning and an intimate understanding of the Linux kernel memory management subsystems. The promise of RISC-V is total control over the hardware, but the price of that freedom is the responsibility to build the very tools that more established architectures provide by default. In the current state of the industry, treating RISC-V as a replacement for ARM in AI applications is a tactical error unless the project allows for significant R&D overhead. It is a powerful, customizable platform that rewards those who have the engineering capacity to dig into the source code and optimize at the lowest levels. The potential for specialized AI accelerators is immense, but the current reality is one of complex integration tasks and a reliance on a software ecosystem that is evolving in real time. Before committing to a commercial rollout, one must verify that the specific core documentation and kernel support are ready to handle the heavy lifting of modern AI. Only then can the promise of open silicon meet the requirements of functional reliability.